Hello, today we're looking at the last section of chapter 9, which is about our last transformation, which is a dilation. A dilation is the only transformation that we study in this chapter that is not an isometry, and that's because a dilation can change the size of a figure. A dilation doesn't have to change the size of a figure, but typically it does. Otherwise, it would be kind of silly to perform one. When you do a dilation, it's always done around a center point or the center of dilation, and you're given a scale factor, which is the letter R, that tells you how much bigger or how much smaller you're going to make your figure. If your scale factor R has an absolute value greater than 1, then your dilation is going to be an enlargement, or it'll make your picture bigger. If the absolute value of your scale factor is between 0 and 1, then you have a reduction, or your figure will get smaller. And in the rare case that you're doing a dilation with a scale factor that has an absolute value equal to 1, that's where your dilation would actually be the same size. So if you take a look at the first picture on your note sheet, they show you the example of a dilation. Here we're looking at triangle ABD, and it's being dilated about this center point, C. They show us up at the top here that our scale factor, the letter R, is 2. That means our triangle is going to get twice as big as the original. So our pre-image triangle ABD, each of the side lengths get multiplied by 2 to give us our image A prime, B prime, D prime. As I said, a dilation is not an isometry. It does not preserve congruence typically. Instead, it's called a similarity transformation. That's because the pre-image and the image are similar. They have the same exact shape, but they are different sizes. A similarity transformation makes the lengths of the sides of your figure different, but it does preserve certain things. The angle measures, corresponding angle measures, will still be the same. Betweenness of points and collinearity essentially means that the shape doesn't change, but of course the side lengths do. When we perform a dilation around a certain point, given our scale factor R, in order to figure out the size of our new shape, we're going to take each length from the pre-image and multiply it by the absolute value of our scale factor. So in this example, AB is the pre-image and ED is the image. So if we wanted to dilate line segment AB by some factor, we would multiply the length of AB by our scale factor, and that would tell us the length of the new line segment, DE. So let's do just that in the first two examples. It says find the measure of the dilation image, or its pre-image, using the given scale factor. So in number 1, if we have a line segment that's 3 units long, and we want to dilate it by a scale factor of 4, that means our image is going to get 4 times as large. So in order to find the length of the image, A prime, B prime, we take the pre-image and multiply it by the scale factor. So here 3 times 4 means that our image would be 12 units long. In the second question, we're given the length of the image. We have to work backwards to get the length of the pre-image. So remember that we would always take the pre-image, multiply it by the absolute value of our scale factor, and that would give us the length of the image. If I set this up as an equation, the length of the pre-image A would get multiplied by this absolute value of our scale factor, 2/5, and that would give us the length of the image, 8. To solve for the pre-image, we're dividing both sides by 2/5. or of course, that's the same as multiplying both sides by 5/2. And when we do, we can see that the pre-image, the original picture, was 20 units long. The next two examples show how to perform a dilation around a centered point that's not on the coordinate plane. As with the other sections like this, it's going to be a little bit tricky for me to do this digitally, but I'll do the best that I can, of course. And I'll also upload this note sheet so that you can see what the actual figure looks like when I'm able to use a ruler to do all of the lines. So if you take a look at questions 3 and 4, it says draw the dilation image of each figure with the center point C and the given scale factor. So in question number 3, we're going to take this quadrilateral. We're going to dilate it with a scale factor of 4. So I know that my image is going to get 4 times as big. And we're going to do that around the center point C. Like our other transformations, we're going to change each vertex individually. So we're going to start by drawing a line from the center of rotation through each vertex. And I'm just going to do them one at a time because I think it'll be easier to see. We're then going to measure the distance from the center of rotation to our vertex. When I did this on my paper, this first point here had a distance that was about 7/10 of a centimeter, or 0.4 centimeters. We take that length from the pre-image and we multiply it by our scale factor. So if I take my measurement, 7/10 of an inch, and I multiply it by our scale factor of 4, that tells me that the image is going to be 2.8 centimeters from the center of dilation. So now I'm going to measure from the center of dilation out 2.8 centimeters to figure out where my new point will be. And you're going to repeat that process for each vertex of your pre-image. So now if I go to the next point, again, I'm going to draw a line from the center of dilation through the point, the vertex of my pre-image. I measure from the center of dilation to that point. This time I got the length of 1.7 centimeters. Multiply the length of the pre-image by 4, our scale factor. And here, this point should be 6.8 centimeters away. That goes pretty far, all the way up about here on your figure. Okay, for the next one, when I connect the center of dilation through the vertex, I measure from that center out to the vertex. This one I got about 1.4 centimeters. Multiply that length by your scale factor, which this one it should end up at 5.6 centimeters. And then you're measuring from the center of dilation again out 5.6 centimeters. Okay, and finally for our last point, from the center of dilation through the vertex, this final point from the center to that vertex, I measured as 0.7 centimeters again. So when I multiply by the scale factor, that one should be out 2.8 centimeters. And I believe that goes about here. When you're finished dilating each individual vertex, connect your points to give you the image. Okay, remember that the pre-image and the image should be similar. So mine is certainly not perfect on my iPad, but you can see this does appear to be about 4 times larger, but the shapes are still approximately the same. For question number 4, we're doing another dilation. This time our scale factor is -2. So I mentioned before that we're always looking at the absolute value of the scale factor, but a negative scale factor changes the size of your image, but it also performs a rotation 180 degrees around the center of dilation. When you're working with a question like number 4, where you're not on the coordinate plane, the difference is that when you connect each of your points, so just like the last question, I would start by connecting each vertex to my center of dilation. But instead of drawing my image down here on the same side of the center of dilation, it's instead going to flip my image to go on the other side of the center. So this time when I draw my lines, I'm going to connect the vertex still to the center, but I extend my line in the opposite direction. Then I'm still going to do my measurements like we did in the last question. So if I were to measure from point C, the center, to this first vertex that I connected, for this one I got 0.8 centimeters. Just like the last question, I take that measurement, 0.8, and I multiply it by the absolute value of my scale factor. So this length is going to become 1.6 centimeters. Once I determine that new length from my center of rotation still, I measure out 1.6 centimeters, but this time I'm not measuring towards the old vertex, I'm measuring in the opposite direction. That's where the difference comes in for our negative scale factor. So I believe this point should end up about here. Okay, let's do that again for another point. So from my center of dilation, I'm going to draw a line to another vertex. But this time I'm going to extend that line in the opposite direction. Measure from the center of dilation to that vertex. Here I got 1.6 centimeters. Take the length from that pre-image, multiply it by the absolute value of your scale factor. So when this becomes twice as big, my image is now going to have a length of 3.2 centimeters. So from my center of dilation, I measure out in the opposite direction, 3.2 centimeters. And that one ends up about here. When you continue that process for each of the other points, let me give you an idea of what this figure ends up looking like. It's not what I wanted. Okay, when you dilate the other points and connect their vertices, the image here should look about like this. It should be a shape similar to the pre-image, twice as large, but notice it's also rotated 180 degrees. Again, I'll upload my note sheet that this is done by hand so that you can see the measurements and what this would look like on your exact note sheet. Okay, when you flip over to the back, we're going to perform some dilations on the coordinate plane. As usual, these end up being a good bit easier. On the coordinate plane, when you're given the scale factor, in order to perform the dilation, you multiply each point of the pre-image by your scale factor, and then you can plot those new points. So in question number 5, it says line segment PQ has these endpoints. Find the image of PQ after a dilation centered about the origin, and we're only going to do dilations on the origin on the coordinate plane, if your scale factor is 1/3. Sketch both the pre-image and the image. So a scale factor 1/3 means that this is going to be a reduction. The line segment should end up being 1/3 the length of the size of the original segment. So I'm going to take the coordinates from point P, and in order to find P prime, I'm going to multiply everything by 1/3. So when I multiply 1/3 times 9, the x-coordinate for P prime should be 3. 1/3 times 0, the y-coordinate is still going to be 0. To get Q prime, I'm going to multiply 1/3 times the coordinates for Q. So Q prime ends up at 0, 2. Graph each of your new points. Make sure you label them, please. And you can see here we have our similar line segments. They're the same shape, sort of the same orientation, but of course the length is 1/3 of the size. In question number 6, we're going to dilate triangle KLM, again centered about the origin, and a dilation with a scale factor of -2. So when we go to find our coordinates on the coordinate plane, we're still going to multiply by the scale factor. We're not talking about its absolute value on the coordinate plane. So to find K prime, I'm going to take our scale factor of -2 and multiply it by the coordinates from point K. So K prime ends up at -10, -16. To get L prime, I multiply -2 by each coordinate from point L. So L prime is at 6, -8. And to get M prime, again, I multiply my scale factor of -2 by the coordinates from M. And M prime will go to 2, 12. Remember, a scale factor of -2 means that my figure is going to get twice as large, but it's also going to be rotated 180 degrees about the origin. So let's plot our new coordinates. K prime is off of the graph. It should be about here. L prime is at 6, -8 over here. And M prime is also slightly off of the graph, only one space. M prime should be up here. When you connect your vertices and compare your pre-image to the image, again, they should have the same shape, but your image should be twice as big and rotated 180 degrees about the origin. Okay, for our last two questions, we are given a dilation performed on the coordinate plane, and our job is to figure out if the dilation was a reduction or enlargement, and then the scale factor that was actually performed. So for question number 7, when we take a look at this graph, First of all, notice that the original, the pre-image, is smaller than the image. So this is definitely going to be an enlargement. The image, P prime, Q prime, R prime, S prime, is definitely bigger than the pre-image. The next thing we have to figure out is by how much. What's the scale factor? To find the scale factor, you determine the length of one measurement from your image and divide that by the length of the corresponding measurement from your pre-image. In question number 7, we don't want to have to look at the lengths of the sides of the shapes because we'd have to use the distance formula. So instead, let's do something similar to what we did in questions 3 and 4, where we measured the distance from the center of dilation out to each point. So if I measure from the center of dilation C out to a point on my image, P prime, I get 1, 2, 3, 4, 5, 6 spaces. So one of the measurements from my image is 6 units long. If I find the corresponding measurement for my pre-image from C to P is 2 units long. And when I divide those things out, my scale factor is 3. So this is an enlargement by a scale factor of 3. In question number 8, when you compare the size of the pre-image and the image, it looks like the image certainly got smaller. So number 8 is a reduction. This time, to find the scale factor, I am going to use the actual lengths on our two triangles, simply because I have vertical lines, so I can count their lengths on the coordinate plane. So this is the other way to figure out the lengths. So from U to V is 6 units long. U prime to V prime is 4 units long. We always divide out the image over the pre-image. So here we have 4 over 6, or a scale factor of 2/3. Please make sure that you complete tonight's homework to the best of your ability. If you don't have a ruler, do the best you can to try and draw out the questions like 3 and 4.